Hello everyone. Sorry for the delay. There's a bit of delay in me bringing out this video because I was involved in a few things. But anyway, and for those who are new to this uh, channel, I am Saptarshi Mukherjee. I'm a software engineer 3 at Google, and I've been a competitive programmer. So in this playlist, we are basically discussing the different problems of Codeforces round 923, and this problem is the best problem of all those problems we have been discussing, of the contests that we have been discussing. This question is based on DP. You can brainstorm on whether this can be solved using greedy algorithms or other approaches as well. We'll be happy to discuss, but for the time being, I'll stick to one approach, that is DP. And in this reference, I'll tell you that a few days back, I'd actually launched one video which was again based on a Codeforces problem. The problem was blocking elements, and I had shown how using some DP strategy, which is very commonly used in many other problems like longest increasing subsequence and many others, we can solve that problem. So here also the same kind of approach, very similar kind of approach can be used to solve this problem. This is the hardest problem in that contest and also the most educational problem. So okay, let's see how we can solve it. This is the question. You have a horizontal strip of n cells, and in ith cell there is a charge of size ai, paint charge, and see it says that the charge can be used to the left or used to the right or not used at all. Used to the left means, so if the ith element is used to the left, in the ith element you have ai, so that means all the cells to the left up to a distance ai. This is the mathematical notation. So ai distance from I up to the left, ai elements at most can be painted. To the right also it's the same thing. And these two lines are important. It says that for one paint charge, you can't paint both to the left and the right. You have to choose either left or right, or you will not paint. And it is allowed for a cell to be painted more than once. So from two different elements, if both of them paints a certain element in between, or if an element gets painted by two different elements, that is fine. So that is not a problem. And what do we have to do? We have to basically paint all the cells of the strip. So every cell has to be painted at least once by at least one element, including itself. But it must be painted. There should be no cell which remains unpainted. Now we have to find what is the minimum number of times a charge needs to be used. Minimum number of times a charge needs to be used for all the cells to be painted. Okay, so let us understand what this means. So you can see I've taken this small example. Let's say at some index I you have 3. If you want this as your painting element, as your paint charge, it can paint 3 elements from here up to the left. That means from I to I minus 2 you have 3 elements. So this can paint 3 elements from here up to the left. It can paint 3 elements from here up to the right. I to I plus 2. So either this part can get painted or this part can get painted by this element. Okay, great. Let us take some examples. I've written some examples here. So if you have 1 1, a single one cannot paint the other one because including, so when I say that this is element 1, it basically means that including this element it can paint only one element, maximum one element. So this can paint only itself. That other one can also paint only itself. But when we have a 2, 2 can paint itself as well as another element. So 2 covers this part. Contiguous subarray. So there is only one element that needs to paint, that is this 2. This 2, there is only one element needed. That is why the count is 1. Over here I need to paint all the 3 ones, but over here only painting this 3 will work. That's why the answer is 1, because only painting one element is going to work. Next, 1 2 3 1 2 4 2 in this particular example, this is also given in the test case. You can see this is one way of painting it. So basically, if I paint only this element, and this element, basically if I use them for painting, if I use the 2 for painting to the left, if I use this 3 for painting to the right, and this 2 for painting to the left, then basically you can see those areas get covered. I've drawn the rectangles to depict that. 2 will cover 1 and 2, 3 will cover 3, 1, 2, 2 will cover 4, 2. Great. Now, the question is how to solve this problem. Going back, I'll look at the constraints. I've understood some of the test cases, that is fine. No need to look at all the test cases at once. In most cases, people don't look at all the test cases. They look at some easy test cases to get some idea. Then they look at maybe one hard test case or long test case. Okay. Now this constraint is interesting. The numbers are very small. N goes up to maximum 100 in a certain test case. Maximum there are 100 test cases, but if n goes to 100, each n is up to 100, the total number of n cannot cross 1000, which means if n is the maximum, that is 100, then there can be maximum 10 test cases. Okay, so that means for n squared definitely it is possible, whatever happens. For n cube is it possible? 100 cube into 10 is quite less than 10 to the power 8. So in that way it is possible. So n cube up to n cube we don't see a problem. Cool. Now coming back, as we discussed, there was another problem I solved around a week back, blocking elements, and I told you how you can solve that problem. For each element, you did not have the surety whether this element will be a part of the answer or not. So what we used is that, hey, take these cases that, okay, if this element is chosen, what is the best answer? In that way, we solved the problem. Here, we can use certain guesses, hypothesis, prioritization to say which elements should be chosen, which elements, if chosen, will give us a better answer. We can do all those things. Those are greedy algorithms, slightly greedy paradigms. But if we have to say, okay, I'll consider all possibilities blindly. Out of all possibilities, I'll choose the best answer. It is dynamic programming that basically enables us to do that. Dynamic programming basically tells us that, okay, at every step, take all the possibilities and move ahead. And for that, I'll proceed with this, that for each element, you have these 3 possibilities. In red, the part that I've written, you have these 3 possibilities. Either you may not want to choose, don't choose the element, or you cover the left, or you cover the right. We already know this. These are the 3 possibilities. And for each element, if I say these are the 3 possibilities, based on that, I can form this kind of a DP state. This is a very common DP formulation where we say, okay, we will go element by element. So there are n rows, and for each row, there are these 3 states. One state is that this last element that you're considering at any point of time, last element, you're either not choosing, or you're making that cover the left, or you're making that cover the right. And for each of these possibilities, I say, with state j, for the last element, what is the minimum cost of painting all the elements up to I? Up to I. That is, forget all the elements. All the elements you cannot think altogether. But consider only up to ith position. Then, for the last element, you have these 3 possibilities. Take any of the possibilities, j. J refers to any of the 3 states. For each of that, up to every I, I'll calculate for every j. I'll say, okay, what is the minimum cost of painting all the elements up to I with a state j? Let us see how it turns out. These are my states. So I'm basically saying that AI, based on what I'm doing with AI, this jth value is basically getting decided. So first, when I say 0, I'm basically saying that, okay, I'm painting up to I, painting all the elements up to I, where we don't choose AI. Next one, for I1, I'm basically saying I'll paint all the elements up to I, where AI will cover the left. That is, AI is being chosen and towards the left. And DPI2 will basically be painting all the elements up to I, where AI covers the right. Okay. Now the question is, will it help me? Will this particular formulation help me? Is this a good formulation? How can we answer that? There is only one way to answer that. We have to form the relationship between these states and the previous states. So there are these are names of approaches: bottom-up approach and top-down approach. Our final goal is basically dp of n. dp of n or dp of n minus 1, whatever. We have to cover all the elements. So that is our final goal, dpn. And our initial part is dp0. That is where we are starting from. So we have to reach dpn from dp0. If we can calculate dpn based on smaller values, dp of I which are smaller, then if we can calculate that easily, then it is a good formulation. If it is very hard to calculate a dp state based on the smaller dp states, then it is a bad formulation. So I'll think, hey, can I calculate this? Can I calculate this or this one in an easy way? If I know dpi minus 1, all the values, if I know all the values up to dpi minus 1, can I calculate for values I? So let us see. Let us start from the last one. dpi2, what does this say? This says that ai will cover the right. What does this mean? This means that if this is I, that means up to I minus 1, ai will not cover. So up to I minus 1, we need the previous elements to maybe cover them. And ai will just focus on its right, on itself and its right. So what is the best answer up to here? If I say up to dpi2, what is the best answer? I can say, okay, this one will contribute 1 for itself. And I can say for I minus 1, up to I minus 1, what is the best answer for me? So up to I minus 1, for I minus 1, what is the best answer? Whatever is the best answer, I can pick that up and I can say, okay, after that I'll take AI. So it basically means that many plus 1. This is my best answer. If AI covers the right, if AI basically covers the right, that means up to I minus 1 it will not cover. So up to I minus 1, whatever is the existing answer, that is dp of I minus 1, that answer will be taken, that is already optimized. We already know that. Okay. Now let us see how the formulations look like. Exactly as we discussed. So dp of I2, 2 means right, it is covering the right. So I'm basically saying, okay, for dp I minus 1, take all the possible states. However way you want to complete dp I minus 1, do it and take the minimum of all of them. To that add 1. Why 1? Because you're choosing AI for your right, for yourself and your right. So 1 for AI and the minimum for the previous elements. This will give you the answer for this one. Full proof, nothing wrong over here. Great. I'll come to this in a moment, this example. Let us see the other two states. dpi1 basically is a similar thing. dpi1 says that, okay, I will cover the left, AI will cover the left. So if let's say this is I. So these are the elements of the array. So let's say this is I, that means 4. It will cover up to 4 elements in the left. That means up to here it will cover. That means I definitely need to plan up to here. I definitely need to plan something up to here. So the minimum of this can help me. Additionally, we say, okay, if you have found a better answer somewhere over here, you are free to take it. If you have found a better answer up to here, this I can cover all these. But if you think that using these elements you have already got a better answer for up to here, definitely use it. So if I say that, okay, this will cover up to here, and this definitely from here up to the back, I need some other arrangement. These values tell me that, okay, up to here that this is the best answer. If I say, let's say there was something even lesser, let's say there was an x which was lesser than all these values over here, I could have taken this, I could have said, okay, I'll choose this answer, and after that I'll basically put this element, so it is x plus 1, definitely. So this is one thing we can easily take the minimum over here and do it. In what case can it help me? Let's say 1, 2, 3, 4, 5. Let's say we had a 5 over here. So I can say that this 5 covered everything. So over here maybe I would have just 1. If it was a element 5, this 5 would have covered everything. So I would say, okay, this covers 1. So I can say when you're placing this 4, the best 4 can do is this 1 plus this 1 plus this extra element you're taking, that is 2. This could help you. Here the other answer is also 2, but just you can imagine such cases when you know suddenly some good element over here can give you a very good element for this particular position. So I'm planning this way that okay, not just I minus ai, these values can be bad. So I'm taking from I minus ai up to I minus I, because I minus 1, because any element over here definitely means that up to I minus ai everything is covered. Any element over here, dp of anything over here and any state after that basically means up to I minus ai definitely things are covered. So I'm taking all these states. All of these states for this j falling over here basically means that I minus ai up to I minus ai is already covered. Up to I minus ai is covered. So after that, I mean, how much is not covered, etc. I'm already taking care of that. This I will take care of that. But if something more is covered by that, I don't care. Up to I minus ai is covered, that is the guarantee. So I'm taking this entire range and also all these states. Okay, and finally, the final state, that is if I don't do anything, if I don't take it, then I have to rely on my left elements, that they have to take me, they have to paint me, which means I have to look at my elements to the left so that they cover me when they are painting to the right. So I need such elements, for example, for speaking about this 1, or let's say for this 2, who can paint this 2 from its left? 3 can paint this 2 from its left. 1 cannot paint this 2, but 3 can paint this 2 from its left. So this 2 is going to be a participant in my answer. This is my right, this is the right, these are the right cases. So for this element, if it paints to the right, this is 2. And I'll say, okay, for 2, if it has to depend on its left elements, it needs those elements who can reach this guy. So from 3, it can reach this guy. For 1, it cannot reach that guy. I plus AI, all those calculations. So you can see over here, it is basically minimum of dpj2. So all these whatever are possible which can contribute, I'm going to take the minimum. And this is my condition, j plus j plus aj minus 1 is greater than equal to I. What is this? Basically, if this is j and this is aj is this element, this can go up to j plus aj minus 1. Now that should be at I or after I, so that I gets covered within that. So j plus aj minus 1. This has to be greater than equal to I. Got it? Okay, so that's it. Now if you see, this is how I have basically filled up this entire table. If you look from the left, first values are pretty easy. You see, what is this for topmost value? It is infinity, basically saying that this is not possible. If I don't choose, D means don't choose. If I don't choose this one, that means it is not possible. So I put the infinity, that is maximum. The cost is maximum. When I say cost, I basically mean the number of elements you need to paint. Minimum number of elements you need to paint. That is the minimum cost. So it is not possible over here if you don't choose one. And if you choose them left or right, you will get the same cost, that is 1, and it is possible. Now with 2, you can see that applying the same formula, I can say, okay, if this goes to the left, then from I minus ai to I minus 1, that means out of these values, I minus ai basically means this index minus 2. So minus 2 means this particular column. So from here, basically the minimum value is 0. So I'll take 0, and 0 plus 1 gives me 1. 0 plus 1 gives me this one. And for the right, I will say, okay, take the minimum value from here and add 1 to it. So 1 plus 1 is 2. Don't do infinity plus 1. So it's the minimum plus 1, right? And so on. This is how all my values are formed. I can take another example, this 4. For this 4, I can say this particular value, this left value will come from, I think we had already discussed this, it will come from, yeah, this particular portion, I minus ai to I minus 1. Whatever is the minimum value in this part plus 1. So it is 1 plus 1, that is 2. And if I say what is this value, that 4, for this 4, I will say okay, can 3 reach this 4? No. Can this 2 reach this 4? Yes. Can this 1 reach this 4? No. So this is the one candidate. There is no other candidate, it seems. So this 3 gets copied over there. Otherwise, we will take the minimum. If there are multiple candidates, we will take the minimum, which is not this case. Finally, in this 2, this is the last element. I will say, okay, this element is basically going to come from the minimum of this. Yeah, this, and there are no other elements. So from here, this guy will come. It will come from here. What else? This 3 is going to come from 2, that is from the minimum of this plus 1. Minimum over here is 2, 2 plus 1 is 3. And over here, this is going to come from the minimum of this plus 1. So minimum of this is 2 plus 1, 3. In this way, I'm getting the last column as 3. So 3 is the best, and I get the same best value by taking 2 or not taking 2. By taking 2 in any manner or not taking 2 in any manner. So yeah. This was one easy example of how I have found a basic DP formulation and solved the whole problem using that. But now there is a trick. This does not work for all test cases. And the example test case is quite good. It basically gives us a case where it will not help. This one. This is the 11th test case as mentioned over here. It gives us a very good case where it will not work. Let us see why. This is that particular example. If you see over here, I have done the entire computation over here and I have found 3. So if I do one quick formulation, we can choose this one as one block, 8 covering all the left, then this 8 once again covering many things to the left, or maybe I can say this 2 covering to its right, and then this 2 also to its left, or whatever you say. So using these 3, I can basically cover everything, and my answer also came as 3, but the best answer is 2. Over there only it is given that the best answer is 2. And this raises the temperatures. How is that possible? Or how could the algorithm miss this? The algorithm seemed so perfect, well knit, that hey, the ith answer gets obtained from the previous answers considering all cases. What case has been missed over here? If I look over here, if we look over here, okay, looks like I have the final form over here. I will erase this. Yeah, I'll erase this, and now I'll ask you, what will be the value over here? This will be 8 plus, okay, without choosing 2. So from uh, you will basically choose the minimum of the previous state. So 3, you can choose this. You can choose this 3. 5 also you can choose. So 1, 2, 3, 4, 5. Yes, 5 you can choose. So you can choose 2. So you get a 2 over here. So I'll put this 2 over here. Okay. Let us see. For this 8. For this 8, if I don't choose this 8, what do I get? What do I get for this 8? I get the same. Okay, so I get this one, and this one. Now I have to check how. Okay, yeah, I get that 2. That 2 can be obtained from here. Okay, next for this 2, if I want to form this, what will be the answer? It will be the so this 3 can participate, this 2 cannot participate because j plus aj minus 1 is not going to satisfy, is not going to have I. So this 3 is going to participate. What else? This 3 is going to participate. This 3 can also participate, nothing else. So 3, 3, all are 3, so I'll get this 3 over here. I don't remember what it was before. But anyway, I'm getting the 3 from here. What case am I missing? I'm missing one case, which is if my 8 covers from here all the elements to the left and my 6 covers all the elements to the right, can I say that this answer should have been 2? My 8 can cover all the elements to the left, my 6 can cover all the elements to the right. So this answer should have been 2. Based on this, I filled up the whole table. Or the whole table you can verify has been filled up using this formula. Where did we miss this? Okay, let us see. So 6 was given the duty to cover the right. Over here 6 is supposed to cover the right. But if 6 covers the right, look what we have written over here. It is 3. It is 3. Is it wrong? That if 6 covers the right, is it 3? Now we are seeing, okay, 8 can cover the left, 6 can cover the right. In 2 elements only it is finished. But we saw that this is 3. Why? Is this wrong? No, it is correct. Because the definition of this state is, what is the minimum cost to fill up to here? Complete up to I, up to this index. For this element, the task was, you have to fill up all the elements up to here. You have to paint all the elements up to here using the elements up to here, using minimum elements up to here. So if you use only these elements, you cannot do anything. You need 3 elements. Only when you reach out to elements like this, then you get better possibilities. But that was not given. And the reason you are having this greater value of 3, that is why you cannot utilize this value over here. When you are asked, when you basically want to form from here to here, you are getting 3. Actually this has a much bigger potential. This can give you a 2 over here. But because this has been formed in a way that it covers only, it uses only elements from the left. So it basically says, okay, for my left elements are responsible. For coloring, for painting this left, the left elements are responsible. 6 is only focusing on the right. 6 doesn't know that from later on, this 8 can come and fill this up. This 8 can come and fill this up. 6 doesn't know that. 6 felt that its left are responsible for the left. And that is one assumption that we unknowingly seem to have made. So let us analyze this case. This was that case. This was that case. So basically, this is I, this is J. It is possible that if J covers the right and I covers the left, the right elements covers the left elements covers the I, it is possible that they may give better answers. They may help covering a lot of elements. They can cover all these elements with just 2 elements, with just cost equal to 2. You have to figure out that, okay, before this element, before I minus AI plus 1, what is the best value? Or you can say once again, before this basically means that from here up to before this J, what is the best value? Whatever is the best value over here, let that best value be X. Then what can we say? That, okay, now for each of these elements, let's say I plus 1 or I plus 2, if I don't want to use them, I can say, okay, before this already is taken care of by X. X takes care of all these elements, all the previous elements, and also some of these elements, though we did not need them, but okay, it takes care. So best means the minimum cost in this particular range. In this particular range from I minus AI is the nearest column that we are not taking. So that is beyond this I and j. I and j are not covering that. So that column definitely I have to take. And I can take some better values if I have later. I'm covering them fine, but if they are covering with better values, I can take them. That's why I'm taking this entire range. That okay, what is the minimum value over here? That is x. Now I can say okay, from here you're getting x. So x covers the back portion, and these two elements cover the remaining portion up to any of these I plus 1, I plus 2, whatever. So x plus 2. Similarly, here also I can say x plus 2. All these elements up to here, I can tell up to here, the last element, up to the last element, we can say x plus 2. What is this? This is the don't take state. That is when we are not taking this state. This is the dp I0 state. If I don't take them, I can easily state them as x plus 2. Now, is it that easy? I mean, I've just said this is one case. Is this the only case? Other cases we have seen that to the left of I, everything is covering them. Only one J. Now it is, so over here it is J over here. So basically this is J and I from the right covers this. Or I can say that I is basically covering the left, somebody else is covering the right. Something like this. Is it possible there can be multiple J's covering the right from the left? I've seen one J. Can there be another J dash? Won't make sense, right? Because then I can choose the better one of them. I can say whichever one stretches better, I can use them. Why should I need both? Right? Because both J dash and J are belonging to such a range that I covers both of them. I covers them to the left. So whichever one goes to the rightmost point, I'll take that one. Why will I take both the J and J dash? Whichever one goes farther, I'll take that. So definitely there won't be multiple cross intersections, something like that. There will be only one cross like that. There is no profit we gain from multiple crosses. Like one comes to the left and then two go to the right. If I've drawn wrongly, so maybe yeah, something like this. Two go to the right. That is not possible. Because in this case, I'll choose whichever one goes to the farthest left. So I'll choose the top one. So that is it. When I understand that, fine, this is the only case I need to apply. So I can gradually, I can directly go and say, okay, whenever you're looking at an I and you're filling up these values, do another thing. Consider every J behind you, and with that J, if you partner in this cross manner, what good can you do? You can basically fill up all these values in that way. So you can take each of the J values before you, partner with them, and see the best values you can form for the I plus 1, I plus 2, and those indices when you're not taking them, for those cases that you're not taking them. That is it. So with that particular case, I can say that yes, now the moment I'll consider 8 and 6, I will say yes, 6 can cover my right. So I'll go to each one of these and say okay, make them 2, because if I go 8 steps backward, I'll get 0. So it is 0 plus 2. So 2, 2, 2. Here I will get this 2. X plus 2. X is 0. So x plus 2 is 2. So I'm basically applying this information, this this step, that for every I, for all the j, for every I, when I'm filling up the I values, dpi values, I'll also consider all the j for every j such that j plus aj minus 1 is greater than I. That means j goes up to at least one element after I, and I goes up to at least one element before j. I minus ai plus 1 is the leftmost element for I to cover in the left. So if that goes at least one element before j, then only there is a point of this entire thing. So if these two conditions are satisfied, then I will basically apply this one, ij. This will give me 2 points, 2 points I and j, plus whatever is the minimum up to I minus ai. That is what I was taking using this yellow window, that for I minus ai, whatever I am taking, that thing. So that this minimum is going to be dp, yeah, this particular thing is going to go up to dp k0 for every k from I plus 1 to j plus aj minus 1. That's it. That's what I had drawn over here. So in that dpk0, this is going to go. So yeah, this is how the entire problem gets solved. First of all, you might have a bit of trouble, first of all, visualizing that, okay, how this particular case solves all the problems. That may take time, but first of all, realize that using that basic choosing approach, you solve 90% of the problem. So you can see how such a weird approach actually comes forward and plays a part in so many DP problems. In Codeforces contests, you will find a bit of twists due to which just using the approach won't give you good solutions. You just have to uh, complete the solutions, you have to complete those pieces. So yeah, let's look at the solution. Let's look at the code that I had written. Yeah, I've done the same thing. I'm going to every I. I've initialized all these elements with 500. I know that the maximum value can be 100, so I've taken infinity as 500. dpi0 is going to be the minimum of the dpi minus 1, 2 or dpj2 values, the minimum of those. I'm checking whether my j is correct or not. We had discussed this, that this is the j condition we need to satisfy. So I'm checking this j condition over here. That if this j condition doesn't follow that, then continue, otherwise, yeah. Then dpi1, we have seen dpi1 for multiple j's and for all the three k's. So that's exactly what I'm doing for multiple j's in that window, and for all the three k's I'm finding the minimum value. What else? Now dpi2, this is simple, just the previous step, I minus 1. So here it is, dpi minus 1 j, all the j's I'm considering. Next I'm considering that thing, okay, I have found out the values for I. Now if I partner I with every possible j before it, what do I get? So I'm considering every possible j, and then I'm saying, okay, int last basically is what is the last element that this I and j is going to cover. So j basically covers the last element, which is j minus aj plus 1. This thing. This is the last element that these two guys can cover. And my back basically is what I'm leaving to the back. That is I minus ai. That is the nearest element that I'm leaving, that I is not covering. I and j are not covering. And now I'll say, okay, if these are just sanity checks, um, that they should be overlapping. Basically, I've translated these two conditions over there, these two rectangular, this thing and this thing, these two conditions over there. Yeah. And next, k equals to, I'm going from back up to j minus 1. So the minimum out of all of them I'm going to take over here. So I'll take the minimum of all those values. And that min back I'm going to use over here, min back plus 2. So min back is not covered by I and j, may or may not be covered. And 2 basically covers everything else other than the back. So yeah, min back plus 2, I'm considering it in my dpk0. Where does k go from? From I plus 1 up to last. And then what is the answer? It is the minimum of all of these. Uh, we can strike out one of them, maybe dpn2 is not needed. dpn0 and dpn1 are sufficient. Because last element going to the right, what does it mean? It can, to the left is also sufficient. So yeah, that's it. I hope you got some valuable insights from this problem. Uh, with practice, these things will develop. With more practice, you can do it fast. With more and more practice, you can basically keep solving these problems consistently during the contest, but things will happen in steps. It is good to take time in the first attempt, understand it completely, and then move ahead to solve it persistently later on in the coming contests. So yeah, see you all in the next videos. I hope you all are regularly participating in contests. I am keen to actually see all of you uh, solve every contest. I'll try to post the tutorials of every contest going forward. Uh, and so wish that all of you will actually give all the contests and then come back and check the editorials, and see if you gain something from the insights there. All the best. Take care. Keep coding. Goodbye.